Okay, students, welcome to video class 45. And in this video, we are going to study about the state space representation of a transfer function. So far, what we have studied in our previous videos is so we know how to find out the state space representation of an electrical system, of a given mechanical system using the physical variables. And we also studied how to obtain the state space model from a differential equation using the phasor method or phasor state variables. And now we are going to study if a transfer function is given, how to obtain the state space representation of that. Okay, so mind you that transfer function is a different approach to analysis, as I have told you earlier in our introductory class of state space representation. Just as state space representation, transfer function is also an approach of analysis. Now, if you are given with the transfer function of a system, you can still derive the state space representation of that. Okay, so far, um, okay, now when you talk about transfer function, we can have a classification of transfer function as the transfer function can be of two types. Okay, that is based on on the uh, on the based on the terms present in the based on the terms present in the numerator of the transfer function. Okay, in the numerator of the transfer function, that is, transfer function can be a transfer function with, say, you know that transfer function is of the form p of s to q of s. Okay, so it is the numerator polynomial is p of s and q of s is the denominator polynomial. You can have a transfer function with p of s to be a constant. Okay, for example, say for example 1 by s square plus 2s plus 3. Okay, example. Another example is 3 divided by s square plus 3s plus 4. Right. All these transfer functions, comes under this category, transfer function with p of s to be a constant. Similarly, you can have a transfer function with p of s to be a polynomial, of s. That is, example is, say for example, you can have s plus 1 by s square plus 3s plus 4, right? This is an example. Then you can have s square plus 3s plus 1 divided by s raised to 4 plus 3s square plus 2s, okay, s cube plus 3. So all these are examples of the second category, where p of s is a polynomial of the s. Okay, so these are the two types of transfer function. Now, if you're given with the transfer function, you will be able to derive the state space representation. Transfer function is also a function which describes a system. Okay, now if you want the state space representation of that system from the transfer function, it is also possible to have it from the given transfer function. Now, based on the categorization of this transfer function, the state space representation can be evaluated using this transfer function, but with the two different approaches. So first of all, let us consider a transfer function with p of s to be a constant. That is case 1. P of s to be a constant. That is the first case. Okay, case 1, we are considering transfer function with p of s to be a constant. Okay, that is, the theory is, say suppose your y of s to u of s. Okay, so this is how we have a, okay, you know this is actually your system. Do remember, I have a recap of that. So this will be u1 of t, u2 of t. U is the letter which we have assigned for input. X is assigned for states, while y is the output. So y of s to k of s may be, say, some k divided by, this is a general expression of this type, right? P of s is a constant, k by s raised to n plus an into s raised to n minus 1 plus up to etc. is 0, right? Now, how will you do this? In this case, what you need to do is, it's quite simple. You can cross multiply this. So on cross multiplying, you will get y of s is equal to s raised to n plus an into s raised to n minus 1 etc. up to a0 is equal to k into u of s, right? Now, how will you get the if you want a state model, you want to get the differential equation. At least you should get the differential equation. Now, is there any method by which you can convert it into differential equation? If you have the Laplace transform in this form, you can have the differential equation. I'll explain. Say it is of the form s raised to n into y of s plus an into s raised to n minus 1 into y of s, right? Plus an minus 1. Sorry, it is an minus 1. An minus 1. Okay. Now next is an minus 2 into s raised to n minus 2 into y of s, right? Etc. up to a0 into y of s, right? a0 into y of s. It is equal to k into u of s. Now, what happens if you apply the inverse Laplace transform? Now, mind you that this is transfer function. Transfer function is a function which we defined p of s to q of s with the initial condition is 0. So, keeping that in mind, you can have the inverse of this, right? When you take the inverse, what is the inverse of s into y of s? S into y of s. Or you can think in this way, what is the Laplace transform of dy of t by dt? It will be s into y of s. And you don't have to, and there is minus y of 0. You don't have to consider this because we are dealing with the transfer function. Because transfer function or this type of transfer function is derived upon the condition that the initial condition is 0. So you just need to mind about this. So what about d square y of t by dt square? What is its Laplace transform? It will be s square into y of s, and it has some more terms. You don't have to consider that because all this represents the initial condition, while since it is a transfer function, this is defined only for the case where initial condition is 0. So what about the inverse of this? When you convert this, inverse is s square into y of s can be written as d square y of t. So if that is the case, how will you convert this equation? So that you will get this is d raised to n of y of t by dt raised to n, right? Plus dn minus 1 an minus 1 into dn minus 1 dt raised to n minus 1 y of t plus an minus 2 d n minus 2 y of t by dt raised to n minus 2 etc. up to a0 into y of s. What is y of s? Y of s is the Laplace transform of y of t, right? The Laplace transform of y of t is y of s. So what is the inverse of y of s? It has to be y of t. a0 into y of t is equal to k into, what is the Laplace inverse of u of s? The Laplace inverse of u of s is u of t. Okay, so this is k into u of t. Okay, now you have the differential equation. Now using phase variables, you can convert it into the state model as we have seen in the previous video. Now what is the method? You need to consider y of t to be some x1, right? Now how how many state variables it will be having. Look at the order of the differential equation. The order is n. That means you can have x1, x2 up to xn. And what will be your x2? X2 will be your dy of t by dt, right? Or that can be assigned as, and that is actually equal to x1 dot, right? All these things which we have studied. So you will be getting x1 dot, x2 dot up to xn dot, and the xn dot you will be getting from this equation. Okay, this is the procedure. So this is a case where the transfer function is a constant. Okay, so we started with this we started with this case. What we do is we represent this as y of s to u of s. Why u of s? Because we have already designated this value u of s as the u of t as the input and y of t as the, so the Laplace transfer has to be y of s to u of s. The y of s to u of s is k by s raised to n. And mind you that this transfer function is defined where with the initial state is 0. So you can cross multiply, and applying the inverse you can take all those things. Okay, and we won't be considering the rest of the terms while especially finding out the inverse. The reason is the transfer function is defined in such a way that the initial state is 0. So you will be able to get the state space representation. Now we are going into the straight away into the problem, right? Now when you write it into matrix form, okay, as I have told you in the previous video, you're going to get a controllable you're going to get a controllable canonical form. Okay, canonical form. Okay, and if you have any doubts, you may refer the previous video for this term. I have explained what is this controllable canonical form. Okay. Okay, so here is a question for you. You are asked to find the state space model for the system having a transfer function this. Now, first of all, when you get a question like this, first of all, you should check the category of this transfer function. So this category comes under this case 1, a transfer function with p of s to be a constant. This p of s is a constant. Now, what you need to do is, you need to cross multiply this so that you will be getting y of s into s square plus s plus 1 is equal to u of s, right? We know that. What is this y of s? Y of s is actually the Laplace transform of y of t, right? And what is y of t? In our state space model, y of t is considered to be the output. And what is the Laplace transform of u of t is u of s. And what is u of t? U of t is considered to be the input of a in the state space representation of the system, right? So you can have this s square into, this can be written as s square into y of s plus s into y of s plus y of s is equal to u of s, right? Now taking the inverse Laplace transform, okay, so from the previous discussion, this s square into y of s is actually what? This can be written as s square into y of s can be written as d square y of t by dt square plus, what about this? S into y of s will be d into y of t by dt plus y of t is equal to u of t, right? Y of s, the inverse is y of t, s into y of s. Okay, so this is what I have explained earlier in this general case. Okay, now this is the differential equation. Now once you get the differential equation, you can assign this y of t, right, one of the output variable to be the state variable x1, right? And what will be the derivative of this? Dy of t by dt can be then written as, this will be called as the x1 dot, or this can be assigned as the second variable x2. Okay, so this is one of the state equations. Then next is how many state variables you have. You have two state variables. Okay, so you need to get, so one state variable, and you need to get the first derivative of the, so you got this derivative of this variable, and you also need to get the first derivative of the x2. Now from where will you get? So since it is a second order differential equation, these are the two state variables. Now how will you get x2 dot? X2 dot you will get from the equation. So this can be written as x2 dot plus, what is this, dy of t by dt? Dy of d by dt is x2. x2 plus x1 is equal to u of t, right? Or you, from this you will be getting x2 dot as minus x1 minus x2 and plus u of t, or this is your x2 dot, right? Okay, now these two forms what? These two forms the state equation. Now how to write the state equation? Mind you that state equation is of the form x dot is equal to ax plus bu, right? Now let's write the so this is going to be a 2 into 1 matrix because there is only two variables. So this is x1 dot and x2 dot matrix. This is equal to, this is a 2 by 2 matrix, or 2 into 1 matrix. This is going to be another 2 into 1 matrix with x1 and x2. So this forms a 4 into 2 into 2 matrix, right? So this is multipliable and this results in a 2 into 1 matrix. Okay, so you can fill it. x1 dot, first look at the first equation. You have only x2, that is 1 0. Then x2 dot, you have a minus 1, right? And you have again a minus 1. Now this is not complete, you have input as well, right? So this results in a 2 into 1 matrix. So you need a 2 into 1 matrix here. So this is going to be another 2 into 1 matrix with 0 and 1 into u of t, right? Because in the first equation you don't have any output, so this is 0 into, then in the next you have an our input, so this is 0 1 into u of t, right? Now now how will you get this? So this is your state equation. Okay, this is very simple thing. Now what is the output? Now we have already assigned y of t to be equal to x1, right? So you can have the matrix equation as y of t as 1 0, okay, into x1 x2. You don't have any x2 here, only x1. So this is how, so this is your output equation. Now this output equation and this state equation both forms the state model for this transfer function 1 by s square plus s plus 1. Okay, hope things are clear. Okay, so here is the second question. Obtain the state model of the transfer function given by y of s to u of s is equal to 10 by s cube plus 4s squared plus 2s plus 1. So here is also you are having a transfer function with the constant p of s. So here you need to cross multiply this y of s into s cube plus 4s squared plus 2s plus 1 is equal to 10 into u of s. Now obtaining the inverse of that, for finding out the inverse Laplace transform, you can you can do like this. This is nice. The next step is q plus y of s plus 4 into s square into y of s plus 2s into y of s plus y of s is equal to 10 into u of s. Okay, now taking the inverse Laplace transform, what you get is this is actually equal to d cube into y of t by dt cube, right, plus 4 times d square y of t by dt square plus 2 times dy of t by dt plus y of t is equal to 10 times u of t, right? Now once you get this differential equation, it's quite simple. Y of t is equal to, you can assign y of t is equal to x1, right? Y of t equal to x1, and so this is y of t equals x1. So x1 is defined as y of t, and how many state variables you will be having? You will be having 3 state variables because it is having an order 3. So you can assign this dy of t by dt as equal to, so this can be written as x1 dot, or this is your second state variable, right? That is your second state variable. So x1 dot is equal to x2. Now next is next you have d square y of t by dt square, and that is actually equal to x2 dot, or that can be assigned as x3, right? So that is your x3. Now next is, now from this, how will you obtain x3 dot? Now you will be getting your x3 dot from this equation, right? So your x3 dot is going to be equal to 4 times, what is d square y of t by dt square? That is x2 dot or x3, 4 times x3, right, plus 2 times x2, right? dy of t is assigned as x2, and then you have x1 is equal to 10 times u of t, okay? Or you can write this x cube dot as equal to, you can bring all these things to the other side, so this will be minus x1 minus 2x2 minus 4x3, right? And this is plus 10 into u of t, right? So this is actually the third part of the state equation, right? Right, and when you write the state equation, you'll be getting this as, okay, your state equation will be like this: x1 dot, x2 dot, x3 dot, right? So that means it is a 3 into 1 matrix. This is equal to, since it is a 3 into 1 matrix, you have a column matrix again of 3 into 1, x1, x2 and x3. Now what is x1 dot? X1 dot is x2, that means this is 1, this is 0 and this is 0. Now what is x2 dot? It is x3, so this is 1, 0 and 0. Look, now you can transform this to matrix again. X3 is minus x1 minus 1 minus 2 minus 2, then minus 4, right? Now this plus, again you have a 3, so in the first two equations you don't have any input, so you can call this as 0, 0, and this is 10 into u of t. Okay, so look at this, and this is what I told you. This always results in a form like this, right? Okay, in the last row you will be having all the coefficients of this, and almost this part will be like this, and you will be having your y of t as, how will you get the y of t? We will be getting your y of t as 1 0 0 0 into x1, x2, x3, okay, right? So you will be getting your y of t as this. So this form is what is called as the, this form is also what is called as the canonical form, okay, controllable. This is called as a controllable canonical form, right? Okay, so here are some more examples: 10 by s cube plus 4s squared plus 2s plus 1, and 1 by s squared plus 2s plus 5. And these two transfer function also comes under the category where p of s is a constant. You may do it by yourself to get an equation like this. Okay, so that's the end of this portion. Okay, so I'm going to give the answer for this. This is the answer for this case. Okay, so you may just do it and check whether you are getting this answer. And this is not available anyway. It's not given. You may just find out by yourself. This is quite simple. Now, if you understood the previous two problems, it's very easy to do these two. Okay, it's quite simple, right? Now next is actually, in the next session we are going to study about the transfer function with a polynomial, with p of s to be a polynomial. Okay.